Welcome to lesson 2 in this 3-part series on mixed model line design. And let me just remind you, if you haven't listened to lesson 1, you can just go up on this page. There should be a button there, and we suggest you watch lesson 1 first because you'll be able to be introduced to the subject, the definition, what it is, a lot of background information we're not going to repeat in this lesson. So go ahead and take a look at that one first. Thanks for your comments and suggestions. And again, there's room below this video to add those as we go forward. So just to review, we've made the point, I think, strongly that mixed model line design is a skill that you as a lean professional, as a manufacturing engineer, as a manufacturing manager, or as a lean consultant even within your company need to have. And it's not that common. There aren't that many places where you can actually learn this stuff, but we've done this how many times? Hundreds, probably?
Hundreds of implementations under our belt.
Hundreds, and we teach this on a regular basis, so this is something we're excited about, actually, because we've seen it work and be successful over and over again. So it's the recipe for how to design a successful lean process or a lean value stream or a lean production line. So with that, we're going to jump right into the heart of the matter in this lesson, which is, what is this process? What are the steps? We're going to walk you through them one by one in just a second.
Now, in this lesson, before we jump into the roadmap, what we want to address is this issue of the more scientific side of lean, which is line design. As you may recall, we mentioned before that there is a 90% to 10% ratio of benefits, with 90% of the financial benefits derived from a line design, while 10% of the benefits are derived from the Kaizen activity. So when you think about on which side of the ledger you want to be on the 90% side, because for one thing, it's going to make you much more valuable, but also because it's much more expensive to fix a bad line design than it is to actually design it right from the start. So focus on designing the line right from the start. That doesn't mean that all the Kaizen training, all the Kaizen work that you have practiced has gone to waste. By no means, but it's much better to start from a solid line design than it is from a broken line design.
That 90% number, we didn't just make that up. That comes from an actual study that was done at Toyota in Japan and documented in the book Toyota Kata, where they describe the details of that study, and that's what they discovered.
Yeah, by the way, do get yourself a copy of that book. Very good book, very well written, very good information. And finally, the other thing we want to accomplish with this series of videos is to look for ways to make you an expert in mixed model line design. We want you to learn the tools, to learn the practices, to learn the methodology, to learn the roadmap, so you become a valued mixed model line design expert in your company. That will increase your value as a professional and will make your job much more valuable to the company.
I mean, I don't know if this is a concern that you have, but if you want to lay off proof your job, then becoming an expert in this area is a good way to do it. Yeah. Because, again, these are skills that add a lot of value. In other words, you pay for yourself many times over by being able to contribute these skills to your organization.
Absolutely. Now, where do these concepts come from? The roadmap that we're going to be presenting to you in just a few moments comes from many hundreds of implementations worth of experience, many thousands of hours worth of experience in mixed model line design and mixed model material management. So those are the two topics that we focus on this series of videos. However, it's just about mixed model line design. And mixed model line design is not new. We're not telling you something about that we invented or that we developed. We are probably some of the most experienced ones out there. We wrote a couple of books on the subject. We have probably the largest number of mixed model line designs in the aerospace industry, but this is not new. Many companies have embraced this. Companies like John Deere, like Toyota, like Boeing, this is the methodology they use. And we are lucky enough to be the ones who have documented it and be training many of you on it.
If you go to our website, as a matter of fact, if you want to see a list of companies that we have there that we've worked with personally, and that's just a subset of the total number of companies out there, you can see the kind of organizations that are actually doing this.
Just the ones that fit on the page.
Yeah. So LeonardoGroupAmericas.com.
So
Right.
let's go and we don't have a lot of time, so let's go and jump into the roadmap. We're going to be walking you through the specific steps for mixed model line design. Of course, remembering that this is a crash course in mixed model line design. We're going to try to cram 3 days of information into a few minutes. But what we want to accomplish with this is for you to see the value of it and see that there is a methodology. It's not about, okay, I need to get me 4 years worth of college to get me an industrial engineering degree. This is a methodology that you can learn and you can apply.
Okay, so if you haven't done so already, there's a report that you can refer to, maybe not right now, but afterwards, that'll summarize what you're about to hear. Also, have a pen, have a piece of paper, and get ready to go. Okay, so we're going to really add additional commentary and detail to the list of steps that you'll see in this report that you can download, and we'll be fleshing it out a little bit more than you have there. So have your pen ready. Not everything's in the report. Take notes. We'll amplify on this. And this is the sequence that we actually follow. I remember one piece of advice, Gerard, I'll reminisce, and it was to us as consultants back in the early days. You know, we did have to start with our first project at some point in time, right? Everyone has a first one. And I remember the word of advice from my team leader, and that was, look, I know this can be confusing. I know you can sometimes feel like you're lost or don't know what to do next. And the recommendation there is go back to the roadmap, go back to the process. Right, follow the steps. And I think I saw that in my own experience when my colleagues would go off the track into the ditch on projects. It was because they didn't follow the process. Exactly right. So we're going to show you the process. We're going to share it with you, but the recommendation is follow it.
Yeah.
Follow it.
Whenever you feel lost, and you will, whenever you feel lost, stop. Go back to the last step and move again. Stay within the roadmap. And one of the first things in the folks that attend class see that they get a copy of the roadmap. And the roadmap is basically a flow chart that flows from the upper left-hand corner in a clockwise motion. And it starts with a series of steps that we're not going to discuss here right now, but I'll tell you, it starts with an assessment. You need to figure out where you are. And from that assessment, we recommend that you do value stream mapping, you figure out the metrics. And one of the outcomes of that assessment is to figure out all the potential implementations, all the potential target areas. We refer to that as a target area because it may be that you have multiple lines. It may be that you have multiple different processes or processes that can be linked and balanced and processes that cannot be linked and balanced and are kept as independent process feeding a Kanban supermarket. So you need to figure out step 1 for this specific section of the roadmap. Where is that you're going? What is that target area that you're going to implement first? Normally what we'd like to do is not a 100% recommendation, but it's pretty close there, is start at the end. Go to the end of the line, start with that last portion of the line that delivers to the customer. The closest you get to the customer, the better read you have of the customer demand. So step 1, identify or confirm the target area. Don't try to do an entire factory all at once, unless it's really small. Start with a target area.
And let's say you don't actually have a new project to work on or an entire line that's being redesigned. And that's very possible, right? That you don't, at the present moment, don't have that opportunity. Well, you can pick a piece of that line, and that would be your target area to work on for improvement. And again, don't pick a piece that's upstream. As Gerard said, start with a piece that's downstream, starting at the end, and work your way up. Because as we like to say, it's easier to pull a donkey. If you have a donkey and a horse, you'd rather have the racehorse in front rather than the racehorse behind the donkey. So if you improve upstream processes, they're going to flow like greased lightning, but then they run into unimproved processes that are slower. That's what you don't want. So if you start at the end, get your end running like a racehorse, and then you've got donkeys behind that you'll have to train later on. But start at the end for that reason. Right.
So start with the target area.
That's
so
number
now
one.
you know your target area. My turn to reminisce.
Yeah.
Long time ago, my dad, industrial engineer too, and he had quite a few clients around the city where I grew up in Buenos Aires. So every now and again, my dad
Not
would
Detroit?
ask. My dad would take one of us, and mostly me, to see one of these places. So we would ride it to one of the factories and go and observe while he was doing some of his work. And I remember driving to one of these places, my dad would say, well, son, it doesn't matter what method you're going to use to design a line. You always have to answer two basic questions. What is that you're making, and how you're making it? So those are the two questions you need to answer now. So step one. So step one was the target area. Step two, figure out the products. So for that target area, you need to go through the entire list of all the products that go through a target area. Now, it may be that you're looking at combining multiple lines. All the products that go through all the lines. Every single one. Now, when we say products, don't think just the products that are going to clear the end of the line. There may be some other products that clear the line somewhere in the middle. Spare parts, service parts, interfactory orders. Any product that places a burden of work on a process, you need to document it. So step two, get your product list. Sounds good?
Okay. So you're building a spreadsheet. That could be a good way to start doing that, right? List your products.
Pretty much. Think spreadsheets. Spreadsheets are your best friends when it comes to this. Now, with that in mind, you have your product list. Now think spreadsheet, right? You have all your products as your rows, and maybe a column for the product description, a column for the part number. Excellent. Add one more column, volumes. Now, volumes easier said than done. What you want to do is to figure out, and here's a decision that needs to be made based on data of what is the capacity that you want the line to have. It doesn't mean you're going to build it. You just want that capacity to be available. So you have your 125 or 686 products, and for each of them, based on history, based on forecast, figuring out the average, maybe a couple of standard deviations up, figure out where you want that product to fall, but then you have to make a decision. All the information that you will gather and all the statistical analysis you will make will only inform a decision. And that decision needs to be expressed in number of units per day for each unit of product. So each product must have a forecast daily volume. That's the word we're using, the term we're using, forecast daily volume. You're going to hear us say FDV, forecast daily volume, per product expressed in number of units per day.
And it can be a fraction. Doesn't have to be a whole number.
Absolutely. If you're making aircraft, guaranteed
one every 4 days, it
exactly.
would be 0.25.
Exactly. A quarter of a unit per day. That's perfectly okay. And as you may recall from the video in lesson 1, you're going to be using that information to calculate the tempo, the rate of each process, that takt time we talked about.
Now I'm going to use a dirty word here, wash my mouth out with soap after I say this, but really the volume is a kind of a forecast. So we're not just looking at past history or what we're doing today. We're trying to be proactive with your volumes. Because remember, you want this design to last a while. And especially if you're growing, you don't want to run out of capacity soon because you didn't think enough into the future, far enough into the future. So it's a forecast of a type.
Yeah.
I think it's
and frankly, I think that the word forecast has been maligned by some of the folks.
Unfairly.
Unfairly maligned by some folks in the consulting industry or in the lean specialty because of the misunderstanding that setting a forecast means running the line to a forecast.
Building to a forecast.
Exactly.
Yeah.
You do not build to a forecast, you build to customer demand, but you're going to be setting the capacity to a decision that is going to be informed by history and by a forecast. So,
Good.
step 3,
So
you have
products,
the volumes.
Yeah. So target area, products, volumes. Right now,
Okay.
step 4.
Step 4, remember my dad? How do you make them? So you go out to the floor and you look for every product on your list. Yeah, I know, that's a lot of work. For every product on your list, you need to figure out what are the processes involved in making that product. Now, processes, that would take us quite a bit of time to work through that. As a matter of fact, that's a good couple of hour discussion in class. But a process, for one thing, you will recognize it when you see it, right? A process is a sequence of work steps to advance a product. Those work steps need to be done at constant volume. Now, when you go out to the floor, you will see processes like stamping and hemming and welding and drilling, assembly, test, pack, ship. Each of them is a process. So you need to go out to the floor and identify those processes, make a list, another tab on your spreadsheet. Make a list of all the processes.
I remember I think it was my very first visit as a consultant to a factory. I went in with another guy who was kind of new, and he looked at me and he said, we'd been to class and everything, but this was the first time we were doing it, I think, in the real world. And he said to me, I think we're in trouble here. And I said, well, why? Why do you say that? And he said, because I'm not sure what a process is. And I kind of laughed because I wasn't crystal clear either. But I think working with it, you'll get that clarity. But again, that's the definition. Like work, sequential work steps happen in the same physical area usually. Constant volume going through that process, and you'll get the hang of it by working with it.
After you do this a few times, you will identify processes pretty quickly. Now, picture what you have now. You have a list of products and a list of processes. Picture those as two buckets, right? A bucket of products and a bucket of processes. Now you need to dip into the bucket of products, pull one product. Yes, I know you started with 686, one at a time. You pull one product and you ask, how do I make this product with the processes from this bucket? So the next step is to build what we call the process flow diagram. We call it the PFD, the process flow diagram, which is basically a flow chart, a fishbone looking diagram that shows all the processes involved in making one unit of product, not a batch, not a ton, not a month, not an order, one product, just one unit of product. And all we're focusing on is the relationship of work. This is not a value stream map. We're not looking for delays. We're not looking for times. We're looking for the relationship of products, of processes to make a product.
Sometimes we use sticky notes, and for each product, just lay it out like you read a book from left to right. Lay out the processes, or on a piece of paper with an arrow in between. So it's a very simple flow chart, but every product needs to have a process flow diagram. Now, good news is they're not all different. So just if you have 800 products, it doesn't mean you have 800 different process flow diagrams.
They had
you could have as few
686.
686. That's the right number. You could actually have as few as one process flow diagram if they're all the same, right? Chances are very good that there are some differences, but you're not going to have 600 and what was it? 86 different process flow diagrams.
So the number is going to be the number of PFDs is going to be between 1 minimum, 686 maximum.
Worst case.
Exactly. Yeah. Worst case scenario. Only one bodes very well for mixing. I don't think you mixed enough. 686, probably pretty tough to mix that many different varieties. Now, you have your pile of PFDs. Now, we recommend you build them all on paper. Don't be messing with the computer at this time. Build them all on paper. You will have time to get them into PowerPoint or Visio or something like that soon. Right now, all on paper. Next step is to start extracting information out of these PFDs, because all of them, You can put them on the wall, you're still not going to get a lot of information out of that collection of process flow diagrams. What you need to do is put them all together in one place. And for that, we're going back to this idea of a spreadsheet. Go back to that spreadsheet. Remember, you had all your products as rows. Now we're going to ask you to add all the processes as columns. Products as rows, processes as columns. So what you have now is a matrix. We're referring this one to the this one as the process flow matrix. And for every row, every product, you're going to document the information from the PFD on that row.
So lay this out in the order of the flow. I mean, that makes it easier to understand rather than alphabetical order. So you lay out your processes in the order of the way that the product is going to flow through those processes. So pack is probably on the far right side, or shipping on the far right side, and then everything else upstream sequentially.
Cutting, bending, machining all the way on the left. All right. So
as best you can.
As best as you can. Sometimes it's not possible. Now, every time a product uses a process, put an X on that cell. So you're going to end up with some X's and some empty spaces, right? So why did we say that you start to extract information out of this matrix? Because there are some algorithms that we teach in class that would allow you to sort these all these rows by process commonality. In other words, the products that share the same process patterns, we want to bring them all together, and we refer to those as a product family. Not product family like our friends in marketing refer to, right? All the lawnmowers together, all the snow blowers together. Not that. These are based on process commonality. Why? Because that is your first indication that those products can be mixed. Products within the same family can run on the same line. Now, this is not the only indication, not the only test, but definitely the first test you must pass. And that is, do you have process commonality? If you have process commonality, this is thumbs up for mixing. If you don't have process commonality, now you have one down. Now, multiple tests we need to pass, but process commonality, that's your first test, your first indication that you can mix.
So audit point, if you're following this process and we come to your factory and we ask you, show us your process flow matrix, and you say, well, we haven't done that, then you miss that audit point, because that's one of the deliverables you would have to have. And of course, to get to that point, you need to have products and processes and the relationship of processes and volumes already done. So it's a nice summary of everything you've accomplished so far.
And that's an excellent point, because many times we get calls, we've been to class, but we went to class a year ago, we remember some stuff, we put together a line design, can you come take a look at it? And we're not clairvoyants. We don't know good line designs just from look at them, right? Especially on a CAD design. We need to understand how you balanced and linked those processes. What were the numbers? What's the data behind it? So it is a lot easier for us to provide very efficient help if you greet us with all the information. Here is your product list, your process list. Here are the process flow diagrams. Here's the process flow matrix. Here's your family definition, step by step by step. And we will know. We will be able to tell you at the end. So I am tying this product to this line. It's flowing this way. It comes out this way. Now I can tell you that's a good line design. And that is what we want to give our students. That is what we want to give you, to help you with not just the training, but with the education, to make sure that you know exactly what points to follow and how to check the steps to know that you will arrive to a safe harbor. Now, back to mixed model line design. You have that matrix, right? Products, processes. X's. Each X now is telling you one more thing, and that is work happens here. Product process. There is work for this product that happens at this process. And what that tells you is you needed to have standard work defined for that product process relationship. So every X tells you standard work. And for that, we're proposing a form that we use. It's a very common form that it's called the standard work definition. Standard work definition describes all the tasks and the times and the quality criteria and the materials, including the definition of non-value added work. So from there, you're going to extract the standard times per product process relationship.
If you don't have this, then boy, that's a good place to start, because whether you're lean or not lean, you still need to define the work. That's a Taylor requirement from over 100 years ago.
Yeah.
So if you don't have that, that's a huge low-hanging fruit opportunity to develop.
Absolutely. Now, you let's go back to the matrix. Can you tell? We'll keep going back to the matrix. Very powerful tool to have this developed in a Excel spreadsheet. Now, you have your products, your processes, your volumes. Based on all where those X's are, that means that a product contributes volume to a process. So vertically, you will add the volumes contributed by all the different products. Of the 686 products you have, maybe only 120 contribute volume to the process hem or the process weld. Only those volumes for those 120 products will contribute to the process weld. You add those, now you have the volume for the process weld. Can you see that? Can you see that the volume for weld is not going to be the same volume as assembly? It's not going to be the same volume as pack or ship. All of them may have potentially different volumes. Different volumes mean now different tag times. We're coming to tag times in just a second. All right? So we have volumes per process. Also per process, you need to figure out the effective minutes.
We talked about that earlier, you may recall. In lesson 1, we went through an example of that, how to do that.
Yeah. And there will be processes that are labor intensive, and in those you will factor in things like lunches and breaks and things like that to figure out the number of effective minutes. There may be other processes that are machine intensive, where maybe lunches and breaks don't count as much if you can stagger shifts. Those are internal strategies that you need to figure out. But you may have to consider things like preventive maintenance on those processes. But the bottom line is that now you have per process, effective minutes, and volume per process. The comparison of the two, effective minutes divided by volume at the process level, now you have tag time per process. Add a row at the bottom of your spreadsheet, calculate tag time per process.
Excellent.
So far so good?
Right?
Excellent. So now we have tag time per process. As you may recall, each X points to a standard work definition. I know it's a lot of work, but it's got to be done. All right? If you want to have a solid line design. You have times. What you need to do is extract the standard time from every standard work definition and replace each X with a standard time. Each X becomes a standard time, potentially more than one. Think of a process that has machine and labor times. So you would replace those. 1X becomes 2 times. That makes sense? So per process, now you need to enter all those standard times, because the next step is comparing standard time per process against stacked per process, and the comparison of these two is going to give you the number of resources. And that is one nugget of gold that we're after in our line design. Because each process has multiple standard times and only one tagged, you're going to have to calculate a weighted average of all the standard times Then you take standard time weighted average divided by takt equals number of resources.
Yeah, I think weighted average was maybe 6th grade math, so shouldn't be too much of a challenge for us, but it is a little bit more complicated than just creating an arithmetic average. So you're weighting the times by the volume.
Yes, and later in the 3-day class, we talk about some strategies to overcome some of the potential shortcomings of using averages. We'll talk about that later. Right now, let us walk you through the straight procedure, straight calculation.
We're getting to the resource calculation now. And let me just give you a simple example of how this works. This makes a lot of sense, how this works. So if it takes, I'll just make up a number here. If it takes 5 minutes to build a product, so that's the standard time, right? So whether you have 100 people or...
So that's stacked. That's stacked.
No, that's work content.
Oh.
It takes me 5 minutes to build a product. So that'd be the standard time, okay? But I want one per minute. That is tacked. So my rate at which I want to build these is 1 minute, but it takes 5 minutes. So then the question is, what if I only had one person? Well, I'm going to get one every 5 minutes. Does that meet the goal? No. I want one every 1 minute. So if I had 2 people, I'm going to get one every 2.5 minutes, right? I'm still not where I need to be, and so on and so forth. So I take that standard time, I divided it by the tack time. 5 divided by 1 tells me I need 5 people. Or if it was a machine, 5 machines, right? To get 1 per minute with a 5-minute work content. That's it. It's not any more complicated than that, the resource calculation. Time, work time divided by tack time.
And you saw that exchange done on purpose. So 5 minutes to build a product, that's tacked, right? There is such a thing as tack time for a product. No, there isn't. Products do not have tack time. Processes have tack times. Products have standard work content, standard minutes. That is the amount of work content necessary to build a product has nothing to do with tack time.
Trick question.
Yeah, exactly. Nothing to do with tack time. Tack time is calculated, while standard time is measured with a stopwatch. Okay? No such thing as tack time of a product. So you have a number of resources for the process final assembly. You figured out that you need 4.6 people. 4.6 people. From there, you need to figure out how many places you need to set up for those people to work. For right now, we're going to say that you will take the 4.6 round up. You need 5 places for those people to work at. Different thing later we'll talk about rounding up, rounding down. Don't worry about that. We're coming to it. 4.6 can have 0.6 of a person. You need 5 workstations. Notice I'm not saying you need 5 people. You need 5 workstations. And the 5 workstations are 5 physical places through which the product will flow. And those must be defined by taking the work content from each product divided into 5 increments. 20% of each product must be allocated to each of those workstations to build the product sequentially. So that's how we distribute the work. That's how we define the workstations, by allocating the total work content of the product divided by the number of calculated resources for the process.
Beautiful. So I hope you're following along and taking notes, but we've done a lot so far. So we calculating the resources is the end result of all the work we've done before that. The volumes, the products, this is what we're trying to get to, because before we can get to a design, a physical factory design, that's really what we need to know. How many workstations do I need? How many machines do I need in my layout?
Yeah.
Right? So we're at a really good point here.
We're really close to the layout.
Yes.
You have the number of resources calculated. You have defined the workstations, and by defining the workstations, splitting the work, things like materials and tools and quality criteria are going to come along with those steps of work. Then what you need to do is to seek to balance the work. And for balancing, there are a series of tools that we use. So it is unlikely that every time you spread the work for a product that, as Richard said, you have 5 minutes of work, 5 workstations, 1 minute per workstation. It's unlikely that you will hit exactly 1 minute, but you have a target of 1 minute. If one product is over that 1 minute target, then what you do is you start applying the balancing tools. And the balancing tools, again, that could be a completely separate class, but the balancing tools in this order are going to be first the elimination of work, then the relocation of work, then the addition of resources or the addition of inventory and time, sequencing. So we're going to have a series of balancing tools that are applied sequentially to bring that work content within the target or to make the process work within the target. So balancing is the next step. Now, with balancing finished, then the next step is to put together what we call a conceptual layout.
Conceptual because we don't want to jump right to a CAD layout, as you might be tempted to do. I mean, we see it often, especially if you know CAD. What you want to do is just fire up CAD and start creating a layout. Don't recommend doing that. Why? Because once you start entering into the world of CAD, you start committing yourself to a particular layout because of all the time and effort you put into creating something, and you don't have enough flexibility to really play with different options, different ideas. So start with just paper cutouts, post-it notes, and just lay out the basic flow. The correct number of resources, right? Correct number of workstations, correct number of machines. You can have a discussion of material access for material delivery. You can have discussions about buffering or in-process Kanbans, all those things without committing yourself too firmly to a particular solution.
Yeah,
right?
Low
really
tech,
important.
Low tech, no computer, and we have had. We don't recommend one specific way of going about this because we've done it in many different ways. I remember designing the line that makes the air conditioners for buses, and after we'd done all the calculations, each workstation was a piece of paper like this, an 8.5 by 11 where all the information was written, and we hang it on the wall. And we had an entire large room with very large chunk of wall that we could use for every workstation. We designed everything on the wall. By the time we moved to CAD, it was a really swift move. Why? Because during this conceptual line design, you're working out many of the details, many of the compromises that need to be made, you're working them out at that time. So then when you move to CAD, it's a lot quicker. So, conceptual line design, ignore all the constraints or ignore all the important constraints and go ideal. If we had no constraints, how would this line look like? And go with blocks. Don't worry too much about it being dimensionally correct. And from there, you will move to a CAD layout, which is the next step. So picture having this conceptual line design on the wall, right? And then bring in the CAD operator, a patient CAD operator, fire up CAD, project the layout, the target area on the wall, and then the marching orders for the team is turn whatever we have on the wall, right? The conceptual line design, and make it fit into the space that has been provided for this line design.
So you do need a CAD design, obviously, at the end of the day.
Of course.
Right. Because you do need a dimensionally correct layout. So you don't get away from that by going to a conceptual layout.
But actually,
just make it faster.
And this portion doesn't take long. I have finished layouts in just a couple of days because there were not too many arguments to be had. The arguments happened already during the conceptual line design, and we had them all documented on paper, just notes taken. And then when we went to put together the CAD layout, it went really fast. So
okay, so I'm looking at our list here, Gerard. We've got layouts and then deployment plan and line live.
Yeah,
I think we've probably talked a while here on this. I wonder if we need to stop right now. We have a deliverable now. We have a CAD-based layout. There's one other thing, though, let me just mention, kind of in wrapping up this topic. What we haven't done yet is tested our design with a variety of different scenarios. And that's, again, a whole nother subject that we're pretty excited about getting into, but not in this particular endeavor. But we are launching a simulation class for line design in the near future, so you could look into that. But that's one other piece that we strongly recommend that we include in this process.
Yeah.
It's just that it's technical, it's a kind of a different subject, but important if you want to test your design based on a lot of different variables and variability, which we haven't done yet. So your brain is probably full at this point. Fortunately, we've documented some of this. We do have a book where we cover all of this information in a lot more detail, because each one of these topics, like volumes, for example, is a whole chapter, as you can imagine. And as we mentioned earlier, we take 3 days to go through this. But if you want to get a little more fleshed out on this, we do have a book we've written on the subject called The Complete Guide to Mixed Model Line Design. Again, available from us or through Amazon even.
Yeah.
But the good news is this process that we just shared with you will get you to about 95% of the ultimate design that you're going to end up with. The only piece, as I mentioned earlier, was this simulation piece that we may want to consider, depending on the risk.
Depending on the risk. There are going to be some line designs, as we mentioned in the first video. Some lines are very simple. 5 workstations, balance that live. Just go out, build them up, and balance them live. Now, if you have a line with 65 workstations and 12 feeders and 5 independent processes and many different products, now we're going to recommend that you do build a simulation model. And as Richard said, all these steps will get you to 95% of the data you need to feed that simulation model. So it's going to get you really, really close. All right. So now, with that in mind, what's next? As we said in the first video, we wanted to tell you about why this is important. This is very important because it's about you and your future and how to make you an expert. You saw the what. We just walked you through the steps, granted, really quickly, even though it felt like forever in video minutes. We walked you through very quickly through the steps. Now, what we want to talk about on the next video is about the how to get there. What are the steps you need to follow to become an expert in mixed model line design?
Yeah, and spoiler alert, it's not just a matter of learning the stuff. You actually have to be able to apply it. So part of the how you do this is going to be, of course, learning the theory and making sure you did understand it correctly, and then actually having an opportunity to apply it. Because that's really where you learn this stuff. And that's where Gerard and I have had a huge, and we're grateful for a huge opportunity in our lives to have applied this many, many times. That's why we're so excited about it. We know this works. But you need that opportunity also.
And this is something we have seen many times over with our clients and our students. They come to class, they learn. The day after class, they know a lot. But every day after that, the level of knowledge decreases. That is what we refer to as the forgetting curve. You have the learning curve going up, the forgetting curve going down. So there are things we want to do to make sure that the knowledge you gained in class, you not only retain it, but you also increase it. So we put together a suite of products, from weekly reminders to tests to coaching on individual projects to make sure that you become an expert. Training is good, but it's not everything. So in the next video, we want to talk about what are the steps you need to follow to become an expert, and we're going to go into a little more detail on that.
Okay, so, comments below.
Yeah, before we go, please
take a minute and let us know what you think. Post any questions you have there too, as well, right below this video. And we'll see you in lesson 3.
Thank you.